So my name is Marcus Levy. I'm Director of AI and ML Technologies at NXP. And I sure wish I wish that I could tell you everything that we're doing, but then you'd all have to sign NDAs and you wouldn't be able to leave the room. But we are working on really cool stuff, as probably everybody is who's doing ML these days. But what I want to present today is more of a high-level view on some of the things that we are looking at least from a public standpoint. You probably will say, hey, I'm doing that too. But anyway, I want to try to keep this open. If you guys have any questions, let's do it. So first of all, how familiar are you with machine learning already? I mean, some of you have been in the sessions previously, so how many people are really new to this area? How many people are not raising their hand? Okay, all right, so I guess just to keep moving here quickly, because there's not that much time, but I guess, what is your favorite ML framework? And if I said, is it TensorFlow? I imagine most of you who are using this, you probably raise your hand and say yes. And as I tell customers when I meet with them, hey, there's a lot of choices out there, but I guarantee you if you use TensorFlow, you're not going to get fired, right? It's here to stay. And how about favorite ML model? Of course, it all depends on what you were doing. And Mark, in your previous presentation, it depends on whether you're doing object detection, segmentation, or recognition, or whatever. Most of the people, when they ask me to do benchmarking, it's, can you run MobileNet? And that seems to be the most popular in terms of just an easy benchmark to run. And then the other question, which you have already kind of talked about earlier, was can you run machine learning on an MCU? And you'd be amazed how many customers or audiences I talk to ask that question and they don't believe that it's possible just because of either the operating frequency or the memory space limitations, right? But we do it. I mean, it's totally possible. Of course, you're not going to run a VGG or some other giant network on it, but you can do a reasonable inferencing with reasonable accuracy and, depending on the application, reasonable performance as well. So I'm kind of doing this in reverse. I just want to see, because I have a lot of slides here and I could talk through them all, but just right off the bat here, are there any questions that you guys might have? No? Okay, nothing. ARM-NN, no. But for CMSIS-NN, yeah, I mean, you can compile it down and use an RTOS, no problem. TensorFlow Lite is the same. I mean, it takes a little while to get it integrated into our development environment and run it with the different IDEs as well as operating systems or RTOSs. So it's a little bit. Free RTOS, Zephyr. Doesn't really matter. I mean, sorry, well.
Because you mentioned that you already support free RTOS and Zephyr. I wanted to know if you already, for example, integrate CMSIS-NN support into Zephyr already.
We haven't done that yet specifically, but it's sort of agnostic. I mean, the operating system, the RTOS doesn't really matter in this case here. We haven't had any related issues to that. Okay, so anyway, thanks a lot for coming. Thanks for the questions anyway. All right, so this is kind of fun. I mean, you look at MobileNet, and this is like, MobileNet is one of the simplest model topologies that's out there today. But yet, there's still a lot of operations that it goes through. The most popular part here is the depthwise convolution. And just this particular version here, actually I can't remember the V2 version, but the V1 version that's similar is 559 million MAC operations. And when you try running that on an MCU, I mean, that's requires quite a bit of horsepower. And I'll show you some benchmark numbers later on in my presentation of how, what we're seeing with MobileNet. And again, going on your talk previously, every model has a different level of accuracy. This is just showing MobileNet V1s. I mean, there's so many variants, and if you go up to GitHub, you'll find these are all available in model zoos, quantized, unquantized. And so where it differs here is you have like it's called V1, and then there's a 1.0 and so the 1.0 and the 0.75 and the 0.50 is the width of the multipliers, and then at the end of this string, you'll find there's an input size of 224 by 224 or 192. So you can vary these things depending on how much accuracy you want to sacrifice. So if you look all the way up at the top, which is the biggest version of V1, the accuracy in top 1 is 70.9, whereas this small one down here on the bottom is 41.5% accuracy, which in my opinion is pretty useless. But this is based upon using ImageNet as a data set, which is 1,000 classes. And if you want to take a MobileNet model that's already been trained and adopt it for your own application, then you can apply transfer learning techniques. Anybody familiar with that? Okay, so nobody trains a model these days. Well, I shouldn't say nobody, but many people don't start from scratch. You take a model that's already been trained. Typically, it's with like a COCO data set or an ImageNet data set that's already, has a lot of the classes recognized. And then what you can do is you take your own data and you do a transfer learning approach on that, where you just say, okay, I only want to have it recognize 10 classes or 100 classes. So you can use that approach to actually increase the accuracy. What's interesting to look at, and again, this ties back to the benchmarking topic, is the GOPS and TOPS. And really, I mean, this is a marketing number, right? I mean, TOPS kind of gives a general guideline for, the class of device that you're targeting. And this is showing some of the traditional cores that are in our devices, like a GC7000 GPU, which is 64 gigaflops. And then we have like a typical ML accelerator, could be somewhere around 2 TOPS to 8 TOPS. And when I hear people talking about 2 TOPS or 8 TOPS or 20 TOPS, I always have to say, well, what are you trying to do exactly? I mean, maybe it's a high performance object detection, right, where you're trying to recognize thousands of objects as you're driving down the road. So maybe for an ADAS type application. And then you look at like a Cortex M33, which is 0.6, and then the Cortex A53s and A72s. So I mean, it's still within the same order of magnitude. But really, if you need super high performance processing for ML, you definitely have to go to some type of an ML accelerator. And that, based on the device, based on the compute unit, you can sort of vary your types of applications. So for like low-end stuff where you're doing single function, here is an example of like a doorbell with a camera on it, and it recognizes an individual person. Whereas at the next level up, you're actually looking at things like face detection or specific object detection. But it's still pretty simple. But then when you start getting into more advanced things where, they have actually cameras in retail stores where you're trying to recognize 1,000 or 100 people at the same time, you need a lot more processing power to do that. Any questions? Nobody's sleeping and nobody's eating yet. So good. Okay. So, enablement for machine learning. So there is a group in Lenaro that we're part of. Several of you may already also be part of this, where we are trying to reduce some of the fragmentation in the industry. And there are lots of options. There's actually too many options. And I find that when I go and talk with customers, most of them are going down the TensorFlow Lite path today. We try to sell them on other approaches because it's not going to be always the most high performance or most user-friendly option. So, it's amazing how many people haven't heard of ARM-NN yet. So we need to start promoting that technology. One way to do that here is, okay, so I'm kind of getting ahead of myself here a little bit, but when you break down all the different options that are out there, you have compilers such as GLOW and TVM and MLIR and et cetera. Then you have the runtime and inference engines like TF and TF Lite and ARM-NN and Onyx runtime, and then you have training frameworks and different types of models. And really, I mean, if, you know what, I mean, ML is kind of new. So when you go and, you know, you go out and talk to customers about this stuff, and most of them don't even know where to start, right? There's just too many choices. So what I think we need to do as an industry here is try to help either through performance or through better education and marketing, you know, help figure out, okay, for a given application, what is the right approach? So one of the things that we're doing, and unfortunately this is the biggest challenge from NXP standpoint, I mean, we make a lot of different devices, from low-end MCUs to high-end media processors, and so we're sort of forced to support not everything here, but most everything here. Because you never know, okay, customers maybe they're gonna favor an Onyx runtime, maybe they're gonna favor using a Cafe 2 model, or they're gonna, so in this day and age, right now, we're still sort of in the early stages of ML. You can't afford not to do something. But I'll tell you what you have to be careful about, because I hear this all the time, is from customers, is like, we don't want a proprietary approach, so we're glad you're looking at all these open source options. The trick here is, how do you take an open source option from a competitive standpoint and make your devices look better than everybody else's, right? I mean, this is the problem of any open source, is it kind of rises the tide for everybody. And so you're always looking for ways of doing back-end optimizations, or maybe you're providing optimized model zoos, or, you know, standard stuff. Well, I guess sort of standard, but it's kind of expected that that's what you have to do to differentiate. Where am I stuck? Oh. Okay, so in selecting an inference engine, which is where we really focus, our approach in general at NXP is the BYOM, which is bring your own model, right? And because, boy, once you start getting into trying to educate people on how to do training and collecting data, doing feature extraction on that data, labeling the data, I mean, that's a whole process in itself, and really that's pretty much the hardest part of doing any ML application, right? But once you get to that point, you need to select an inference engine, and you know, there's quantitative and qualitative metrics here. On the qualitative side, of course, you know, it's, hey, I've already used TensorFlow for the last 5 years, and boy, it's really a lot better now, especially with TensorFlow 2.0 that just came out. But you know, from an embedded standpoint, you're really going to be interested in performance and optimizations, in terms of accuracy, in terms of energy consumption, the memory footprint, you know, and all the types of other features. And this is really cool about ARM-NN, is they keep adding more and more functionality to this. So I don't know, how many of you really believe ARM-NN is going to be successful? Come on. It's amazing. I mean, it's only been out for a year, and every 3 months there's a new release. I think some of you were in the previous, not the previous one, but a little bit earlier today. I mean, there's a new release of ARM-NN every 3 months, and every 3 months we see really significant features that come about. And I don't know, we haven't benchmarked the latest 1908 version, but between 1902 and 1905 version, performance went up a lot. So, I mean, it can't continue at that trend indefinitely, but it's really becoming a pretty high performance, not just in terms of, you know, latency, but I mean, overall, the feature capabilities that it supports is pretty cool. By the way, I'm not trying to plug ARM here. I just know there's a few ARM guys in here, but it is. You know, good job, guys. All right, so this kind of goes into a little more detail, well, not a whole lot, on some of the different options. When we first started on this path, you know, OpenCV was pretty much the only choice. And so we did deployment with OpenCV. Pardon my expression, but it kind of sucks, right? I mean, performance is really not that good. You know, any Intel people in here? Probably not, but you know, OpenCV was invented by Intel, and so when you try to start running ARM devices on it, yeah, there's some support for neon acceleration, but try running a non-ARM, a non-Intel GPU. It doesn't do very well, right? And some customers still use that because they like the other features that are provided by OpenCV, But performance-wise and everything else, it's just not the most popular. I don't promote it all that much. This kind of gives you an idea of where, so we have this framework, or not necessarily a framework, but a collection of tools and libraries and stuff that we call EIQ. That's our branding. But I'm sure it's probably pretty similar for a lot of people here. So there's TensorFlow and there's Glow and there's ARM-NN, some OpenCV in there, and we don't really target this towards devices per se, but we look at how do we address different compute units that are inside the device, right? So like TensorFlow, it's cool because you can run it on Cortex-M, on a DSP, on Cortex-A, on GPU, on ML accelerators, right? So it's got a lot of variability to it. And then when you add the devices, this kind of gives you a range of the devices that we support, from low-end MCUs. Actually, some of these are not so low-end. Like this is 600 megahertz MCU, this RT600, which is, we announced it a few months ago, but it has like a Cortex-M33 in there plus a DSP. So for an MCU, I mean, it gives pretty good performance on a machine learning model. And then there's some stuff on here that I can't share. But we're going down some really cool paths here. But this kind of just shows that there's a lot of different options across the board, and what we're trying to see is, okay, is there a method that will work from low end all the way to high end? And then also related to your benchmarking story, we were trying to do, how do we compare apples to apples? And actually, one of the questions I was going to ask you, but maybe I'll just raise it here as well, is you were saying, okay, if you're trying to do a TensorFlow model and then an ONNX model, do you start with the same TensorFlow model and then convert it to ONNX, right? Or do you go to the ONNX model zoo and you go to the TensorFlow model zoo and you pull off a mobile net and you say, well, I hope these are the same. Maybe they give similar accuracy that kind of helps to, ascertain that, but is it still apples to apples? Or is a customer really going to go to TensorFlow, because there's probably more models available in a TensorFlow model zoo, and then you do a conversion. So it's really gets kind of cumbersome, but I was looking at this more of an ideal sourcing scenario. So where do my original models come from, right? Do I take TensorFlow, convert to ONNX, run it with Glow or the ONNX runtime, or do I do a conversion to TF Lite, and then I can take that TF Lite model and run it with ARM-NN, or I can have a TF Lite model that runs as a TF Lite runtime, right? So you can see that the combinations here, it really starts to get interesting. So since everybody knows here about ARM-NN, I'm going to skip this slide. And I will almost skip this slide, except I just want to point out one other advantage here of OpenCV, which kind of doesn't really relate to the ML. Well, it does relate to ML, but doesn't relate to neural networks, is that OpenCV also has classical machine learning algorithm support. So if you need to do SVM or random forest or some of the non-neural network-based ML approaches, then OpenCV still is a good solution for that. And I can't say a whole lot about this. This is something that we're developing right now where we actually, so some of our devices have GPUs in them that only support OpenCL. And one of the things that we're working on is taking TensorFlow Lite and being able to make OpenVX calls to an OpenCL GPU. And so we've written some clever kernels that actually does the translation. So you can talk to it in OpenVX format, but it actually makes OpenCL calls to the GPU. And we're also in the process now of taking that same approach with those OpenVX kernels and hooking them up to ARM-NN. So hopefully in the next couple months, we'll be able to share some of that and have some cool performance results. And then, how much time do I have? I'm hungry. All right, so these are all normalized because I would be fired if I showed you real performance data. So the rest of the presentation, I do have some more performance information, but it's all been normalized to protect the innocent. I think maybe the most interesting ones here, well, Linnet MNIST, not really that interesting because it's kind of small, especially running on an A72. But like ResNet 50 and VGG19, this is comparing ARM-NN, and smaller is better, right? So you can see the difference. And actually, this is old data, so the new version of ARM-NN, I think this was done on 1902. So it's probably significantly different than it is now, than it's shown here in this table. But anyway, I mean, this by itself makes the point, hey, if you're really concerned about performance, don't use OpenCV. And by the way, your mileage does vary, because you can see like the VGG, which is a really big network, the delta is much more significant than the difference between ResNet 50, which is still big, but in comparison to VGG, it's not. All right, so deploying TensorFlow Lite. This is a whole class in itself, and actually we have some videos on our website and some labs where it goes through the process. But the cool thing is that Google provides all the tools to do it, and they also provide some there's also back-end support like Eigen and GemLoP for doing matrix optimizations. My team has done some special matrix optimizations on top of that with some loop unrolling and some other types of things. And on the next slide shows some of the performance differences. This was run on an MCU, so we use smaller benchmarks like Label Image and Cyfar 10. But you can see here, this stack here is Label Image, or these are both Label Image, and these are unoptimized and these are optimized. So you can see that there's about a 36 to 57% improvement based on these additional optimizations that we've done on the back end. And then you could also, what's also highlighted here in the colors are different versions of GCC, and then IAR and Kyle compiler. So you can see that even the compiler makes a difference, which is, you know, if you've been in the benchmarking world for a while, you know compilers have always made the difference as well. And here it holds true as well for these ML benchmarks. All right, so a little bit about quantization. So what you see here on the right-hand side, I'm sure you can't see it in the back, but this is size in megabytes, but it's been normalized. So the purple one here is based on a TensorFlow from the TensorFlow Model Zoo. And then the gray one over here is a TensorFlow after it's been, actually, no, I take that back. So the purple one is TensorFlow Lite, or they're all TensorFlow Lite, but one is before conversion and one is after conversion. And the point here that I want to make is like, okay, so whether I convert the TensorFlow Lite model myself or I get the TensorFlow Lite from the Model Zoo, the size is the same. And the same thing is true for the two quantized versions. But where it gets interesting is on the performance. And basically what this slide is showing here on the latency side is that if I do quantization during training, that the performance of the quantized model is significantly lower, whereas if I do post-training quantization, the performance is really bad. Now your mileage is going to vary a little bit, right? But for the most part, this was a pretty interesting revelation that we discovered, sort of by accident, but you know, after going through the process, it really highlights the fact that if you can, do your quantization during the training process.
And is it just quantization? Is there any other optimization?
There was no other optimizations on that.
I think it might be if you only do post-training quantization, you can only do floating point inference, right? So your inference is actually done in floating point. It's just your weights are stored int. That's why the performance is so bad, because you're doing still floating point operation.
This,
and then you have to add the overhead of actually converting your weights during inference.
that's true.
Yeah, that's why it's actually worse than the floating point model.
You can use a quantized runtime.
What is the content?
You could have a runtime that actually has ops that are processed in a date instead of in floats.
Yeah, so that's what the training quantization is, right? So when you do quantization aware training, you can actually make sure your inference is properly quantized as well. So you're actually doing integer inference rather than floating point.
Yeah. Okay, I'm going to keep going because I only have like 97 seconds left. All right, so because of the time, I'm going to skip this. This is just a description of what CMSIS-NN is. And this is provided by ARM. But just to show you a little bit on the performance side, this is CMSIS-NN compared to TF Lite, and smaller is better, right? But this is on a SciFar 10 model, pretty simple model. Once you start getting into mobile nets, then you can't really use CMSIS-NN anymore because it doesn't have the operator support yet. Who in here is working on CMSIS-NN from ARM? All right. The other thing here is on memory utilization. So again, CMSIS-NN is significantly more efficient on memory utilization than TF Lite. I mean, CMSIS-NN basically boils down to a binary that you can create, whereas TF Lite requires a runtime. So it has to support all the extra overhead with that runtime. Another interesting thing that we're working on is called GLOW. And you know, there's, as I mentioned previously, there's GLOW and there's TVM and there's MLIR, and right. So I mean, there's different options. We chose to go down this path for one main reason, is because our initial evaluation said for MCUs that this provided the best approach, at least at the time, because it allows you to create what's called an AOT version, ahead of time compilation, and it basically spits out C code that you can compile down to a static image, and you don't have a runtime associated with this. So it's basically just taking a graph and creating a series of the computational model out of it, and it's small, right? It only pulls in what you need. When is that coming?
I think the basic support is there already.
Okay, yeah, we're actually working on that right now too. So, but anyway, I just want to spend a couple minutes more just talking about this. So, you know, the cool thing also about GLOW, which is similar for TVM, is it relies on an LLVM backend, so you can take the compiler itself and then tie in specific kernels or optimizations for your own platform. And we did this. We actually took GLOW and we connected it to CMSIS-NN. The cool thing about it is, and the way I kind of look at this is like, you know, CMSIS-NN doesn't support all of the operators, right? It only supports 7 operators. And so if you're running like a MobileNet model and an operator's not supported, it would just compile natively, right? It'll just do a native compilation to ARM. And that way it gives you the flexibility to run other models besides the simple SciFar or some of the simple keyword spotting type algorithms that it was intended for. And so, you know, ultimately, if you started writing more optimized kernels for the back end, you could get better performance out of this. But, you know, this just kind of shows for a Linnet and SciFar 10 using GLOW compared to CMSIS-NN. You know, we're pretty much at par on these with CMSIS-NN by itself, right? To me, that's like the most optimal for that particular model. And same thing is true for the memory footprint. And we actually did a customer use case where they provided us their data. And they said, we want to use a MobileNet V2 model, and we put it into a blender. And the mixture came out. It was a MobileNet model that was trained with the customer's data. We did the TensorFlow, well, we created the TensorFlow quantized model. We converted it to Onyx, and it allowed us to run it on GLOW. And we actually saw a 400 millisecond inference time which is not fabulous if you're looking at, you know, high-end processing, but for an MCU, this was pretty good. But compare the 400 to the same model that we ran with TensorFlow Lite, which was 1400 milliseconds. So it was significantly faster using this GLOW approach with CMSIS-NN. And on top of that, we were still able to get 98.2% accuracy with this MobileNet model. In this case, well, this was just on an M7, one single core. Yeah, I mean, just natively it runs multi-core. But now the next level is, can you do heterogeneous processing? And supposedly the answer is yes. And I mean, ideally that's where we would like to get to, is where you could start balancing off, you know, because some of the layers or operators may run better on a CPU than it does on the GPU. Or, well, once you start plugging in real ML accelerators, that's always going to be the winner. But on all the legacy devices that don't have ML acceleration, and you want to split CPU, DSP, CPU, GPU, heterogeneous processing is potentially a good answer, but it's also very device specific and it's also very model specific. And this is just a high level talking about GLOW versus TF Lite. I mean, it's basically what I've been saying. It's like GLOW is a static image. But actually, GLOW also gives you the ability to do a runtime version, so you could have more flexibility for adding in new model parameters and stuff. But, you know, GLOW is, or any type of, you know, when you can compile the code down versus having a runtime, is always going to be a delta. So I'm at the end here, so any more questions? Yeah, yeah. From my perspective, or NXP's perspective, GLOW is targeted at the microcontrollers. For the higher end processors, you know, I think the support provided by ARM-NN is, we don't need to go past that. And we're not going to beat the you know, that whole open source movement, right?
What are the use cases you have seen when running a classification, image classification network on an IM7? So for microcontroller devices, why would they need to be able to recognize images?
Wow. Okay. That's a hard question to answer without NDA. I'm trying to, you know, there's a lot of ML applications where a second or 2 seconds even inference time is, who cares, right? I mean, you put...
I know some use cases, for example, in the refrigerator, right? You needed to know if some, for example, fruits or maybe some vegetables are empty or not. So you can have some MCU in the refrigerator to detect, right? Yeah, it is not so...
Well, that's one thing, but you know, let's say you put food into a microwave oven, right? All right, you close the door. By the time you walk away from it, it's been 2 seconds, and you've already identified that it's a hot dog or a piece of pizza. So that's one of the examples.
But do you have price advantage for putting an M7 instead of, say, a K7?
Absolutely, for sure, or an A53 even, right? So in embedded world, it always comes down to cost and energy. Okay, any more? Oh, okay. A lot, yeah. Yeah. Well, well, definitely image applications are sexier than sensor stuff, right? So that's where everybody is looking at for state of the art. But this whole thing about classical machine learning algorithms, like you could do probably what you're talking about with an SVM, which is a lot easier to train. It requires a lot less data to do the training, and it takes a lot less compute power for it. So sensor applications, whenever I have a customer that asks about that, my first thing is like, hey, let's look at classical ML to solve this problem before you start looking at a neural network. But yeah, I mean, if you want more information about it, I could talk to you. Yeah. Yeah, no, it's a really good question. So yeah, on the accuracy side, that's hard to answer. What's going to be more accurate? Where it starts getting more interesting and where you may tend to go more towards a neural network with sensors is if you're doing complex sensor fusion and you're trying to look at multiple sources simultaneously. But for what you were just describing, I mean, it sounds fairly straightforward. Yeah. 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 But the classical ML, I mean, you don't have to come up with your own algorithm there as well. I mean, you use the framework that's available.
At that point, feature extraction becomes important.
Yes. Then feature extraction becomes much more of a critical thing. It's like, okay, what am I looking at here? What is the important data? And then this also relates to anomaly detection, because with anomaly detection, you're not looking for the anomaly to happen. You're actually training it to recognize all the good states, and then when there's some deviation from that, then it recognizes that. Because, like, let's say you're using anomaly detection to tell when a motor's going to break. You know, 99.99% of the time that motor's not going to break, so you'll never be able to generate training data for that. So you train it based on known good, and you have to decide how much variation can I have in that. Like the SVM, some of you may be familiar with it, you know, it uses a hyperplane approach. So, you know, you can have like how far off of that hyperplane can I tolerate in my application? Because things will deviate over time, or temperature, or whatever, right? Okay, is that it? Thanks for staying so long.